Hey class, this is 6B problem. So uh, as you can clearly see, this is not actually part of the problem. So what this is excuse me, a way for me to show you the whole quantum number thing is something that we've learned already. So take a look. It says electron configurations, the main energy levels, we call that N. Then we have the sublevels, that's the S, the P, the D, the F, and then we have the orbitals to the sublevels. So S has only one orbital, P has 3, D has 5, F has 7. These are all things that you guys know already. The principal quantum number is exactly the same as the main energy level. Exactly the same. So it's a small whole number from 1 to 7. The azimuthal quantum number is exactly the same as the sublevel. So the difference is that here S equals 0, P equals 1, D equals 2, and F equals 3 for this number. Okay? So the magnetic quantum number goes from negative L, which is what I'm talking about, the azimuthal quantum number, negative L to positive L. So let me write that down here so you can see it. Negative L to positive L. For an example, if L equals 1, then I have negative 1, 0, and positive 1 as my magnetic quantum numbers. So if I have a P sublevel, and we've seen this already, if I have a P sublevel, okay, I have, like if I'm talking about the 2P, then I have a Px, a Py, and a Pz. Or I can call them -1, 0, and +1. So all I'm doing is giving numbers to these things that we've already learned. And then finally, the last one is obviously the easiest one because it's talking about spin. You guys know for the electron spin that we call that a +1/2 or a -1/2, or we use an up arrow or a down arrow, or an up half arrow and a down half arrow, like when we show an orbital diagram that looks like this. But over here, the spin quantum number is, of course, just what you've seen before, which is a +1/2 and -1/2. So I'm going to show you how this stuff all fits together now. So now that I've given you some parameters, let's talk about what it looks like when we put this all together. So the first question says, give the values of N, L, and M sub L for each orbital for the 2P sublevel. Okay, well we can do this because we have the N, L, so I'll do the N, the L, and the M sub L like this. So the first thing I do for the second main energy level, and that N equals 2, my L is going to be, so if N equals 2, I'm going to erase this then, my L is going to be either 1, 0, or 1. And when it's 0, that means what I have then is, okay, now think about this, this would be the 2s. So we have two sublevels in the second main energy level. We have the 2s and the 2p. So the first one here is the 2s. M sub L, if you remember, goes from negative L to positive L, and there is no negative or positive 0, so it's just 2, 0, 0. Okay? Now that's the one orbital. So this would be, what you see there is the 2s. Okay? 2, 0, 0. Good. Now let's move on to the second main energy level, and we're going to go to the first P orbital, which would be the 2px, let's say. And that would be a 1 here for L, because P equals 1. And then we'll start off with the first orbital, will be a -1. And then I'll do the same second energy level, same sublevel, which is P, and then the next orbital. Okay, this one would be the 2py. Okay, and then the last one would be the 2pz, and that would be 2, 1, then you guessed it, a +1 like that. Okay, so these are the 4 orbitals that are in the second main energy level. Okay, so this is going to ask each orbital in the 5d sublevel for B. Okay, again, I'm sticking with my letter N here. I'm going to put a line here, but it's still going to be N in line here, so it's going to be 5. Okay, now what is it? Do you remember what I said they are? The L equals 0 for S, for P it's 1, and for D it's 2. So that means this is going to be a 2 here, because it's asking specifically for the 5D. And since the 5 is a 2, I'm sorry, since the D is a 2, then the D goes with the L here. Now the first one here, remember it goes from negative L to positive L, which means I'm going to go from negative 2. Okay, what is this asking for? Each one, so there's going to be 5 orbitals, because D has 5 orbitals. So each one's going to start with a 5 here, each one's going to start with a 2 here, and then I'm simply counting up like this. 5, 2, positive 1, and then the last one is 5, 2, positive 2, like that. And that's how it works. Okay, so it takes some practice, it takes some like repetition to get the idea as to what's going on, but these are the quantum number questions. So just follow along with me, and hopefully, like at some point, it will make a little bit more sense. I know it's confusing at first. So let's move on. So 58, with reference to the figure 618, what's the relationship between the number of nodes in an s orbital and the value of the principal quantum number? Well, that's pretty simple, because the number of nodes equals whatever the principal quantum number is minus 1. Okay, how do we know that? Because at the 1s, there are zero nodes. Okay, that means there are no spots where from the nucleus till like to the further out you go where electrons don't exist. So they exist everywhere in between here for the 1s. Now here is what we call a node, though, where we have a place where there are electrons, and then on the other side there are electrons, but then all of a sudden we have a node here, and there's only one of them for the 2s. So n minus 1 means 2 minus 1 equals 1 node, like that. And then you can see it again, 1, 2 nodes. So if n equals 3, that means 3 minus 1 equals 2 nodes. Okay, so those are the places where the electrons do not exist, in the 1s, the 2s, and the 3s sublevels. All right, so let's keep going. I don't mean to go too fast, but try and keep up. Excuse me. I've said this before, I think, somewhere, but take a look at this picture of the p sublevel. This one would be the pz orbital. And take a look how fuzzy it looks, and all they've done is say that within so much degree of probability, they can say that the electron will be inside the green 95% of the time, and then this is the shape that gives you 95% of the time. So these orbitals are actually fuzzy. They're not hard-lined like you see here. So we always draw them hard-lined to give a very specific shape, but when in fact, like it's more like a cloud. So that's what we're talking about with the probability thing. Just to explain that. Let's keep going. Oh, I missed some of those questions. So let's take a look. Let me open up a book here and answer some of those questions, and then when we're finished with 58, then I'm going to start a part 2 of the problem set. So let me just get to 58. So the other part, so that was A for 58 with reference to 618. B says identify the number of nodes, that is, identify places where the electron density is 0 in the 2px. So the 2px would be this one over here. The 2px would have a place right at the origin where there would be no electrons. Okay, so this would be at the origin of our graph. So that would be for 58b at the 2px. That's the only place where the electrons would not be outside of that shape. 58c says what information is obtained from the radial probability functions in figure 618. So figure 618 is still this one. Okay, so this right here indicates our highest probability of the electron would be somewhere close. The radial just means radius of the atom. The wave function squared is obviously a very complicated physics term that we're just going to consider to be like, where would we expect the electron to be? And at these places here, here, and here, we would expect them to be there 0% of the time. So what information is obtained from the radial probability functions? On 618, all you have to worry about is that there are no nodes or places where we would not expect to find electrons in the 1s, but the 2s has one node and the 3s has two nodes. Okay, those are it's almost like a repeat of the first question. And then D says, for the hydrogen atom, list the following orbitals in order of increasing energy. And this is very simple. For hydrogen, we have the 1s and then 2s and 2p all together, and then 3s, 3p, 3d all together, and then the 4s, 4p, 4d, and then 4f all together. So it's based solely on the big number in front, okay? Based solely on the big number in front. So that means that, there we go. We would expect the 2s, 2p, 3s, 4d, and 5s to come like that. Now, if we were talking about something other than hydrogen, okay, other than hydrogen, then that would be a little bit different, because we would actually have the 2s, the 2p, so this is hydrogen, and this is other than. And then I would do my diagonal rule or follow the periodic table. 3s comes next, 4d would come after the 5s. And I know that because if I look on a periodic table, the RB and SR come before Y. Y is in the 4D, and RB and SR are in the 5S. So that's the only change that would happen if it would be other than hydrogen. But hydrogen goes directly by the big number. We simply count up from the big number. Okay, thanks for paying attention. We'll pick up after 58 in part 2.